G'day, in this video I'm going to be introducing a lot of concepts that we're going to be focusing on when analysing the motion of objects on inclined planes, and eventually this kind of data is going to be very helpful to us so that we can unpack the forces that are being applied to objects when they are moving on an inclined plane. For this video in particular, we are focusing on the last dot point of inquiry question 1, 2.1.4. So this is going to be the last thing that we're going to use to start talking about how forces can be produced between objects and the effects of those forces. Content statement in particular is that we need to be able to conduct a practical investigation to explain and predict the motion of objects on those inclined planes. So our learning intentions is to be able to use vector diagrams to determine net force for inclined scenarios, use F equals ma to find acceleration. But then also what we're going to start doing is looking at how we can collect some simple kinematic data such as displacement and time and use it to be able to find other unknown variables using those kinematic equations. Once we have something like acceleration, that can be quite powerful to then be able to find force. And that's going to be sort of our bridge between what we've already learned about with kinematics and now what we're starting to focus on with forces and dynamics. Now, when I have an object on an inclined plane, there are many forces that are acting on that object. The first one that we should be able to pick out pretty easily is the force of gravity, so Fg. We can also say that that would be equal to the mass of the object times g, which is the acceleration due to gravity. Remembering from our data sheet that that is 9.8 meters per second squared. The next one is what we call the normal force. So this is usually labeled as Fn. And Fn, again, is what we call the normal force. In this case, it's the force of the inclined surface on the block. So if we recall Newton's third law, that with every action force, there is an equal and opposite force being applied. Essentially, that here is the normal force. There is a force of the block pushing in against the surface of the incline, and that surface is then pushing back up against the block. Now, in a non-inclined situation, let's just say that the block was sitting on a table. This would be a lot easier to see and understand in terms of Newton's third law. So we would have Fg, the force of gravity of the block, pushing down onto the table, but then we would also have the normal force, Fn, pushing back up against it. Now, something to keep in mind that when we're on an inclined plane, there will still be two forces, however, they won't be necessarily equal and opposite in the same way as they were before. And that's because Fg is always directly down, but the normal force is always perpendicular to the plane itself. So technically, what we have here is another force that we can show, which would be Fbs. So the force of the block on the surface of the incline. And this would be equal and opposite to Fn. What we could possibly say here is that Fn is equal to Fsb. So I'm just doing a rewrite here. The normal force here is the force of the surface on the block, and that's equal to negative Fbs. So the force of the block on the surface is equal in magnitude but opposite in direction. There are two more forces that we need to account for. The first one is this force here of friction. And then the actual force that is going to cause movement on the block. And I'm going to show you later that's actually a net force between the force of gravity, the force of the normal, and the force of friction. So let's open with a little bit of a practice question. In this case, what we have is a sled weighing 50 kilos. It's sliding down a frictionless incline of 50 degrees. We're being asked to calculate the acceleration of the sled. Now, I have made this frictionless to make the problem a little bit more straightforward. So we're just focusing on the effect of the normal force and the gravitational force on the force that's being applied to the sled. So for this question, what I'm going to do first is draw out a bit of a diagram showing what's going on. So in this case, we have a normal force, an Fg, which is calculated by mg. I've just multiplied my 50 kilos and the acceleration due to gravity, which is 9.8, giving me the number of newtons of the downward force, or the gravity force, being 490 newtons. I can then do some vector addition between the normal force and the gravitational force to then calculate for the net force. Now, something to note here is that the incline and the net force are going to be parallel to each other. And that is because the overall force will make the block slide in a parallel direction to that of the incline. Now, because FG is always going to be perpendicular to what we assume is a flat surface that the incline is sitting on, that's going to mean here that this angle is 15 degrees, that the angle that's inside the triangle is going to be 90 minus 15, which is 75 degrees. Another assumption that we can make about these angles is that Fn and Fnet are going to be perpendicular to each other. And that is because Fn is always perpendicular to the surface that the object is on, and we already said that Fnet was parallel to the surface, making them effectively perpendicular. Now, with this information, what we can assume is that we can solve using right-angled trigonometry. We know that Fg is equal to 490, and that's going to be the hypotenuse of the triangle. We want to find Fnet, which will be adjacent to our non-90 degree side. So with all of that in mind, I can start to solve. I can say that cos of 75 is equal to adjacent over hypotenuse. Cos is what we want to use because, again, Fnet is the adjacent side and Fg is the hypotenuse. From here, we can begin to sub in. So we can say that cos 75 is equal to Fnet over Fg. We can then move and solve for Fnet, which is equal to Fg times cos of 75. That's going to be equal to 490 times cos 75. So that is about 126.8 newtons of force. We then also need to do a little bit of work to try and figure out what the bearing is. And to do that, I'm going to draw two sets of perpendicular lines which run north-south. We then have our Fnet vector, which essentially works as a transverse line. We know that this is 75 degrees. We know that then, of course, that because we have a pair of alternate angles, this is also going to be 75 degrees, meaning that our bearing here from north to the Fnet vector is going to be 180 minus 75, which is equal to 105 degrees. And that's going to be our true bearing there. So here in our final answer, we can say that the net force is 126.8 newtons, and the bearing is going to be at 105 degrees true. However, the question does not ask us for the net force at the end, but instead how much that the sled is actually going to accelerate. Now, we know by Newton's second law that F is equal to ma, meaning that the acceleration of an object is going to be equal to the force that's placed on an object divided by its mass. So in this example, we know how much force is being applied to the object. It's simply Fnet. That is the resultant force that's going to be put onto the block that's going to cause it to move. So we can actually substitute that straight into our equation. So that's going to be 126.8 newtons of force divided by the mass of the object, which is going to be 50 kilograms. As a result, the object is going to accelerate at approximately 2.54 meters per second squared until it gets to the bottom of the incline. Now that acceleration is going to be parallel to the direction of the force, which means that it's going to be accelerating at 2.54 meters per second squared, but at a bearing of 105 degrees true, and that's going to be the direction that it follows. Now, it is important to note that when we give our final answer, however, we do need to match the lowest number of significant figures given in the question. And for this one, it's actually just one significant figure that we're being given to. So we need to be giving an approximate estimate of the acceleration, and to one significant figure, it's actually going to be 3 meters per second squared. So not a particularly accurate answer that we're giving, but based on the data, that is what we need to provide in the question, because one significant figure was given. Again, we can give our bearing at 105 degrees true. Now, when we get into class and start doing some practical work, what we're going to try and do is calculate acceleration just using displacement and time. And there's actually a couple of algebraic methods that we can use with our kinematics to be able to solve it. So there is one method that I'm going to show you where you can use average velocity to be able to calculate acceleration. There's one where we can use a kinematic equation to calculate for acceleration. Part of the challenge of that practical is that you're going to be trying to figure out how you can actually do that. And what we'll do is write up an algebraic solution here in these slides so that you can have a copy of them. In the next video, what we're going to be doing is looking at static and dynamic friction. There's actually two types of friction depending on whether or not the object is or isn't moving. So yeah, we'll unpack that a little bit and start applying some of those concepts in the lessons that follow.